Alright, you guys, take two. Just got done with leg day in the Church of Iron on a Saturday morning rather than a Sunday morning. Usually do legs on Sundays. But I have a lot that I have to do this weekend, and as a matter of fact, I was like matching with people on Hinge, thinking, oh, let's go out to coffee, whatever, meet up with people. It's the whole dating app fatigue thing. It's like, I am so sick and tired of that BS. All of the so-called successes that come from dating apps over the last however many years, throughout my 20s, they've been short-lived and very disappointing, and in retrospect, a lot of it has to do with just the system of meeting people through dating apps. And it's like, I was like, I have a lot of stuff that I have to 3D print this weekend. Like I was talking about in some of my last videos, how I have to 3D print a Scotch yoke because I can't use the stepper motor for my experimental apparatus by itself to produce an oscillatory output, because the stepper motor will have residual EM energy inside of its internal coils, which, in order to change the sign of the angular velocity on the stepper motor output, you know, it's like the intermediate value theorem. You have to cross zero, and getting that zero, the holding torque in the motor, causes a delay in the electronic control signals. So I was like, okay, I have to make this mechanical solution so that the stepper motor is always going in one direction, and the mechanical solution produces the oscillatory output. And then I can at least vary the speed, the magnitude of the angular velocity. I don't even think, this is like a sign that I'm not a physicist and I'm a mathematician background instead, but it's like, I'm pretty sure that angular velocity is a vector, okay? But you know what I mean when I'm saying, if it's a scalar, whatever, but the magnitude of angular velocity I can at least vary so that it'll always be going in one direction, but I can change how fast the motor's going, and it'll still be oscillating my plastic protractor attachment that has the magnet on it that's swinging through the coil. That's, by Faraday's induction law, it's inducing the current in the coils that I'm then measuring. So I was like, okay, I have to make this mechanical solution, and I was looking at like a 4-arm crank lever situation. But then I was like, okay, well, the angular velocity of each direction of the oscillatory output on a 4 crank bar apparatus, either you have to get the geometry of the lengths perfect and it's only good for one angle that it sweeps through, or it's going to be faster in one direction, slower in the other. And so I was like, okay, I'm going to make a Scotch yoke. I drew some different designs, and I looked at, things online, and I was really inspired by the mechanism of a metronome, because a key thing about this is that my plastic protractor arm is not like huge. It's not like on the scale of like meters, but it's not like a normal size protractor or smaller. So it's not like micro centimeter scale. It's like, a 9-inch radius plastic protractor. So then when I was like, okay, I'm also going to have metal bolts and washers and stuff like holding the pieces of the plastic protractor together. So this stepper motor is going to have to produce, when you think about it, a considerable amount of torque when it's swinging it. And so I was like, okay, if I make this Scotch yoke with like smaller parts and more parts, then there's a higher chance that it's going to break or buckle or something like that. So I was like, I need to make a simple design with fewer parts, but it still has to be kind of like robust enough that it can handle swinging the protractor arm on my apparatus the way that I want, right? So I finally designed that, and I was able to make one that has a variable, adjustable output angle that it sweeps through. It's discrete, not continuous, because if it's continuous, there's more of a chance that it can slip, and I would have to do more measurement when I'm collecting data in order to make sure, like there could be more, there could be like a deviation not bias or deviation, maybe like variance. The variance is greater because I could think that I'm setting the output of the Scotch yoke to be like 45 degrees, let's say, but then really maybe it's like 44 degrees, like 43. So by getting the trigonometry exact at 1/10 of a millimeter scale, I have implemented in the design so that there's a lower inherent level of variability. Variance isn't the right word, right? Because, standard deviation, variance, those are like terms of art in statistics, but you guys probably know what I'm saying, right? So it's not, I can't set my Scotch yoke as I've designed it to output all continuous, values between 0 and 60 degrees, let's say. I just made it so I could do like 10, 15, 20, 25, etc. through 60 degrees. And then another part of so that's one thing to 3D print, is like the Scotch yoke. But then I'm like, okay, how am I going to mount this on my retort clamp stand? And I mostly, up to this point, I've entirely relied on off-the-shelf parts, so to speak. I've just gotten it all from Amazon. And one of the problems I encountered was that, one, the mounts on the stand itself will sometimes slip. Okay, so that's one problem. Two, I put these vice clamps on the mounts that are on the stand, and they're these like angle brackets, and then there's the vice clamp going through the parallel clamps of the bracket, and the metal of that like C portion of the vice clamp, the metal is not exactly at 90 degrees. It's more like the angle between the two is closer to 100 degrees. So there's like 5 degrees in each direction. So like I put another mount on my stepper motor, and then I put that in the vice clamp, put the vice clamp on the mount for the retort stand, and then the motor is like sagging, basically. It's not exactly like parallel with the ground, the axle of the motor. So I'm like, okay, I also have to make a mount for my motor that compensates for that 5 degrees. Otherwise, there's going to be like tension in my Scotch yoke when I put it all on here. The other thing is I'm like, how am I going to actually mount the output of the Scotch yoke? Because I put the stepper motor on one mount, and it's like, okay, well, I need another mount onto the retort stand for the oscillatory output from the Scotch yoke. So I'm like, okay, I have to make something for that and compensate for the 5 degree whatchamacallit from that. But okay, so that's basically 2 things already. Scotch yoke, which is multiple parts, the mount for the output of the Scotch yoke, that's 2 parts, a new mount for the stepper motor that compensates for the angle of the clamp, that's 3. And then I was like, okay, I have these circuits, right? Because I'm driving this using my laptop, controlling a Raspberry Pi, which then over GPIO and I2C, I have my analog to digital converter ADC. I have my stepper motor driver, and now also I have an op amp so that I can amplify the range of the induced voltage in the Hall sensor, which is getting the magnetic field readout as the magnet is swinging through the coil, right? My original plan was I'm gonna put this Hall sensor inside the coil so that the highest voltage is when the magnet is directly in the center of the coil, right? And it's the lowest when it's at the greatest angle in either direction of the oscillatory swing. But then I was like reading these data sheets, I was playing around with the magnet, and I was like, okay, I have an N52 half-inch diameter, half-inch height cylindrical, neodymium magnet. This is like, I don't know what physicists use for their units, whether it's Gauss or Tesla. It's like 65 Tesla or 65,000 Gauss is the strength of that magnet when it's like a few millimeters away. Axially, the pole is head on to the Hall sensor. So I'm like, okay, I need a more sensitive, bigger magnetic sensitivity range Hall sensor. But even then, the max of it is like 176 millitesla. So I'm like, okay, I have to figure out how to make this magnet be farther away from the Hall sensor and then amplify what's actually getting picked up so that I have like greater like data range of my signal, so that's not like compressed down in this tiny numerical range. So I'm like, okay, I'm going to add an op amp into this. So that's an ADC, an op amp, and a stepper motor driver, which are all on a solderless breadboard, okay? So I've got a Raspberry Pi, and then I've got this solderless breadboard with these electronic components, and these are all connected to my laptop, okay? And I'm using an Ethernet switch, but I'm like, if I could just make a little board enclosure with a lid for the Raspberry Pi and this solderless breadboard, then that would make this setup a little more robust, okay? So I'll have the board enclosure box with a lid, made that, Scotch yoke, stepper motor, mounting bracket, like a mounting plate for the output of the Scotch yoke. And then, like I kind of mentioned earlier, I have this plastic protractor attachment, which is going to be swinging, and the stepper motor is going to be responsible for providing the torque to do all of this. And I am using currently metal screws and nuts to hold the pieces of this plastic protractor together. And the metal actually makes a difference in how heavy this is. So I was like, I'm going to just 3D print some plastic screws and nuts, and it'll be lighter, and that way it doesn't have to require as much torque in order to drive this thing. So I had to 3D model like, half a dozen at least. There's like 8 or 6 screws, 6 nuts, the mount brackets, the Scotch yoke has like 2 parts plus a screw and 2 more nuts to fasten it together. And so that's easily, like, I'm not counting in my head because it was just leg days, my excuse. Someone take my degree in math away, but that's over a dozen parts. And the board enclosure, just the box itself minus the lid, the estimated time from the 3D printer software is like almost 7 hours. So I was like, to bring this all back to what I started talking about, I was like, I'm just going to ghost and unmatch with these people on Hinge. They don't even seem like they're like, you're just another option at the end of the day, right? So it's like, I have all this stuff to 3D print. I've got bigger things to do, and I only have so much time to do it. So I have a lot of 3D printing to do this weekend.